go ahead and share that. Okay. So the data sheet is we'll wait for that to open up. It's coming. Yeah. So I'm gonna walk through and we'll walk through and talk about this. And so all this, I answered this yesterday at the end of class, but we can talk about it now since we haven't started yet. The data sheet itself is going to be due next week, but it's already, after today, it'll be fully filled out. Yes. Why this is not showing. That's all right. Move this down. So we've already filled out, excuse me, all of this stuff: molecular weight, density, melting point, boiling point, required amount, actual amount, number of moles, and limiting reagent. We picked which one was the limiting reagent, and we used that down here to calculate the theoretical yield. We took the limiting reagent, multiplied it by the aspirin molecular weight. That gave me theoretical. Today we're going to get the actual, and I can give you those numbers right now. Let me just pull up, and I'll send this out later too in an announcement. But I can give you the numbers right now, so hold tight. So it depends on what sample you've been tracking, because I know every week when we meet, we have a sample that we track. And I'll say, if you want to use sample 1 or sample 2 or sample 3, yada, 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 like, then, you can take the numbers associated with that sample. So if you've been using sample 1, the mass is 6.76 grams, the actual yield. And then if you've been using sample 2, the actual yield is 8.12 grams. And if you've been using sample 3, and the actual yield is 7.14 grams. And the reason I'm saying that is because and these numbers are in the chat, but on the Word document right here where it says actual yield, you pick one of those numbers to put it there. And then you can calculate your percent yield based on that. The percent is actual over theoretical times 100. I'm gonna put that in the chat too. So percent yield, actual over theoretical times 100. That's how you calculate that. So you need this actual, and if we were doing this in person live, you would get the actual yield after the purification. Because if you recall, I know we had 2 weeks, a 2-week gap, but if you recall, last time we met, we were talking about recrystallizing or purifying aspirin. So once you purify it and let it dry, when you come back, you take the mass, and that's your actual yield after purification. So you'll put that into here. Good question. Can somebody help with that? I can't remember the actual number. What did we have for the moles of limiting reagent? Anybody? Somebody should have that on their data sheet already. I just can't remember the exact number.
It was oh wait, hold on. The most 0.05.
105. And which one was limited? Was it acetic anhydride or salicylic acid?
Salicylic acid.
Okay, thank you.
Well,
I'll put that in the chat. I appreciate that. So we know these numbers. We calculated everything. You can calculate the percent, right? So when you turn this in on next week, because the midterm exam is also going to be next week, it's open. It'll be open on Monday. It'll stay open till Thursday. So you have from Monday to Thursday to take that exam. And it's open notes. It's on Blackboard. So there's no excuse. You heard it first here. It's the 24 people in here right now. Put it in your calendar that the midterm exam for this class is going to open on Monday. It's going to close on Thursday. And you have that whole time period. You don't have to wait till Wednesday to take it. You can take it Monday. You can take it Tuesday, Wednesday, or Thursday. It doesn't matter. But you'll have from Monday of next week until Thursday to complete it. We filled out this part with the recrystallization, how much ethanol was used, what the crude yield was. Gave y'all those numbers already. You can fish them out of the announcements because I know I sent an announcement with the crude yield for each sample. How much time it took to dissolve, hot gravity filtration. That was no for everybody, but we discussed that. So today we're going to fill out this backside of the data sheet, and that is the purple color test, the iron chloride test, and then pH testing, and then the melting point. All that's contained in the walkthrough that we're doing today. So once we finish with this, you can turn this in. If you want to turn it in today, that's fine. But you'll have until the day of your next class, which will be next Wednesday, the 12th. You'll have until the 12th to get it submitted. But once it's filled in, you can turn it in. And please don't turn it in with anything missing, because we've had time to fill in everything. So when you turn it in, it should be complete. There shouldn't be any missing data. Yeah, so let me share my screen again so we can everybody see the my web browser?
Yes, we can see it.
Okay. All right. So today we're going to walk through this aspirin the purity walkthrough. And so with the aspirin, I think I sent you a video dealing with talking about how to conduct a melting point experiment, which we'll talk about later in a few minutes, and then how to test for purity. Right? There's a test you can use by adding dilute iron chloride to an aspirin sample that's dissolved up in ethanol. And so what that iron chloride does is, if you add it and there's any salicylic acid left over in that solution, which you should have seen in the video that I sent out, if there's any salicylic acid left over in the solid, it's going to turn purple, right? If it turns dark purple, that's bad. If it's faint, then you could say that it's pure, but it may not be as pure as it could be. Because I've seen some samples where it didn't turn purple at all, right? Some recrystallized samples are so pure that there was no evidence of salicylic acid being left over, right? And the reason I say that is because if you look at the reaction scheme, I'm not sure if you can still see if you can see the Word document back up. Let me know if you can't. Or if you're still seeing YouTube. All right, but if you look at the reaction scheme, you can see right here But salicylic acid plus acetic anhydride will give you aspirin plus acetic acid. So if this reaction didn't go to completion, there should be some of this left. That's how you test to see what's left. It won't tell you how much. It'll just tell you that it's there. It's a qualitative test, not a quantitative test, right? But the quantitative test is the NMR. And let me say this too before we start. So with the NMR and the infrared, those labs are actually functional. And so I want to do those in person. So I'm going to break y'all up into groups, and maybe it may take more than one group or more than two groups, but we'll break up into groups and we'll come and do those experiments. The NMR is actually a very good experiment, and the instrument is it's close to it was $275,000, I think. Very precise, valuable instrument, and it'll allow us to determine like the carbon hydrogen framework of aspirin. That's how most of the times if you make an organic molecule, that's the best way to confirm that you have it is by taking an NMR. Well, I'm going to send you an NMR overview video, all that stuff prior to us doing that lab. So, but anyway, let's go back to YouTube, and then we're going to just get started. Of course, I'll interrupt as it goes. I'll pause and interject and make some comments also. So this is testing for aspirin purity. So we're going to do pH, iron chloride test, and the melting point all in this walkthrough. All right, so you can see, I don't know if you're able to read that, but you should be able to see the numbers underneath there. They kind of got washed out. So we're going to add some salicylate, some iron chloride to each one of those to see if it turns purple. So I'm going to add it first to the crude because I want to see what happens with the crude. And I only need a couple of drops. It's crude aspirin. That's the aspirin. Okay, so the crude aspirin is the aspirin that was not purified. That's what it means when you hear a sample is crude. What that means is that it hasn't been purified. And you can see, let me see if I can get a better frame. Right, you can see right there, when you add that iron chloride to that crude aspirin, it looks like grape Kool-Aid. And that's bad. What that means is that there's a lot of salicylic acid left over. Right, so that's why you have to recrystallize the aspirin to get rid of all the impurities. Right, so that's crude aspirin dissolved up in ethanol, and you can see immediately that it's not very pure. There's a ton of salicylic acid left over, just judging from how dark the purple is. All right, let's move on. See how purple it is? It's full of crap. That's what you don't want. So now we know what we don't want to see. So I'm going to add this same iron chloride. I'm going to add a drop to pure salicylic acid to see what happens there. Hopefully you can still see that. So I'm going to add one drop, 1 or 2 drops to just pure salicylic acid. You can see right away how dark it is. All right, and that's what you expect. Because in the video, it said that the iron chloride forms like a complex with salicylic acid and it turns purple. So you can see that. Can y'all see that? So the plain pure salicylic acid also turns deep purple. What you don't want is for your aspirin sample to look that color. You want it to be lighter than that. The lighter it is, the less salicylic acid is left over after you purify it. So let's see what this is sample 11. You can see immediately that first sample 11 on the end, can y'all see that? All right, so if you're tracking sample 1, if you've been using sample 1 from the beginning, when we did the crude yield and recrystallization and actual yield, this is a very clean sample. Now, if we take an NMR of this aspirin sample, there probably is still some salicylic acid left but the purple is very faint, right? It's not dark like this, like the well next to it, and it's not dark like the crude. So this would be considered a good sample. So where it says on the data sheet, whether sample 1, if you're using sample 1 on your data sheet, where it says within limits, you can put yes. Right, there's a point, I think it's 0.15% limit of how much salicylic acid can that the aspirin can contain, pure aspirin. So where it says within limits, you can say yes. And then where it asks for the color, if you're using sample 1, you can just say very faint purple. Right. All right. Questions about that? Any questions? All right. All right. It's not, it didn't turn purple at all. It turned like a very. You have to purify it again. All right. I'm going to do 30. 30 got a little more purple in it. Can y'all see that? You see 30 on the left, second row on the left, compared to the last. So if you're using sample 2 and you're filling in your data sheet based on sample 2, this is the what you would put in that iron chloride testing table, right? You would put that it is still faint, right? So still faint purple. Is it within limits? Yes. This is also a very clean sample, but you can see compared to sample 1, which is up here, it's a lot more purple. So it's not as clean as sample 1, but it would still be considered a clean sample. And let me ask this question, and anybody can chime in here. What would you do to, or what could you do if your aspirin sample was darker than that, and you wanted to get it pure? What could you do? If you wanted to make the sample more pure than it already was, what could you do? Anybody? What did we do to get it to this point? Purification wise, what did we do to get it to this point? Okay, you said to retest it. Yeah, okay. What if, so how do we purify it to begin with? That's the question. What method was used to purify it? Now, I know it's been 2 weeks, but we just talked about it a second ago. So if we recrystallized it and it was still dirty, the best thing to do would be to recrystallize it again. And most of the times, if you're dealing with this on an industrial level, if they're not using some other purification method, they'll just recrystallize it more than once. All right. Or if it's within limits when you do recrystallize it and do other analytical techniques, because you're not just doing an iron chloride test at an aspirin factory, right? Because it's not accurate. It's qualitative. But if you quantitatively test it and you see that the limit is less than or equal to the accepted limit, which is 0.15%, then you don't have to do anything. But if you did have to, if it didn't meet the limit, then you would have to retest it, recrystallize it again. So recrystallize it. So again, sample 2 is here, and it is slightly darker than sample 1, but it still falls within the limits. Well, at the top right, 30 is a little bit darker than. Darker than the other ones. Can y'all see that? See the difference? How 11 is like really like faint, and then 30 is a little darker, and then 106 is very dark compared to both of those. Can y'all see that? So this is 106 here. So this would be for sample 3. If you were using sample 3 in the data sheet where it says, is it within limits, you would say no. It's too dark. It's almost as dark as the crude that's over here in the top left corner. Right? It's almost as dark as that, and that's not good. So again, if you have a sample that looked like that, and you had time, and you were actually doing this to make this aspirin pure enough for someone to ingest, then you would recrystallize it again. And this is 30, and this is 11. You can see 11 out of those 3 samples, 11 is the purest out of all of them. All right, any questions about the purple color test part? All right, so now the next section is dealing with the pH. This is fairly, go ahead.
So I'm filling in my thing. It asks for 2 color of the crude aspirin. Do I just put in 1 or? Say again, it asks for the crude? The color of, it's asking twice of the color of the crude one.
Hold up 1 second.
On the data sheet.
Mm-hmm.
Do I fill in both of them?
Columns? You can just fill in 1 column. That's fine.
And then what's the iron chloride test? Or
that's what this is.
Okay. So what do I put?
Hold up. Let me pull up the data sheet. Is this is the data sheet that you're looking at, right?
Yeah, that one. Yeah.
For the color of crude aspirin, you can just put yes right here. Where it says iron chloride test, just write yes or type yes. And then where it says color of crude, you could say that it's dark purple, right? Because if you look at the color right here, this is the crude compared to the other samples, which are here, here, and here. This is much darker. So you can just say dark purple.
What about I did sample 3? So I just put this dark purple still?
Yes, or not, because it's not as dark as the crude. You can just say moderately darker than the first 2 samples or something to that effect. Because it's not the same. If you just say dark purple, then that means it's identical to the crude. So it's a little bit lighter than the crude, but still impure. That's a great question. And then if you're using sample 3, then right here, where it says, is it within limits, you're going to say no.
Okay. Thank you.
Yeah. Good question. Good question. All right. Any other questions?
Yeah, I have a question.
Go ahead.
I don't remember which sample I used, but I have the number. Where can I find the samples?
Okay, what number do you have?
Because we're looking under the where is it? The crude yield of the aspirin.
Okay, what did you get for the crude yield?
7.27.
Okay, hold up. I might have to dig through the announcements on Blackboard because I know I sent out that which was which. So let me see.
Oh, then I can look for it then. If
hold up, I might be able to scroll back. Let's see. Oh, that's at the very beginning. Yeah, so that was that would have been sample 3.
Okay, thank you.
Yeah, sample 1 was 7.23 grams. If you had that as your crude mass, then you're working with sample 1. Sample 2 was 7.20 grams as the crude mass. And then sample 3 was 7.27 grams as the crude mass.
Thank you.
No problem. All right, let's go back to here. Any other questions? Feel free to ask. This is it's an open forum. You can ask whatever you need to ask before we move on. So the next part of this is the pH, and you learn pH in general chemistry, right? It's the hydrogen ion concentration And if you have an acid, you expect a high concentration of hydrogen ions, and aspirin has a carboxylic acid functional group present. So you expect the pH to be within the range of the pH for an acid. So you're going to see that there's a panel on the front of the pH paper container that has the range on there. So let's look at that. The color code for the pH. All right, so we're gonna use that. Carboxylic acid in that aspirin molecule. So you expect. So this is why aspirin is acidic, right? And it would be even more acidic if we were to test salicylic acid, because then this wouldn't be a acetyl group, right? It would be an OH. That was one of the main reasons that Felix Hoffman actually tried to figure out a way to convert salicylic acid into some other more palatable compound that could be ingested without irritating the esophagus, because salicylic acid is an irritant to the esophagus and to the stomach. And I think that, as the story is told, he did this to help his father, who suffered from some type of inflammatory disease. And then, of course, salicylic acid, which aspirin gets converted into in the body. Salicylic acid is an anti-inflammatory. So he ended up synthesizing this compound to make it easier to ingest. And then once it's in the stomach and the enzymes and the acid starts working on it, it cleaves off the acetyl group and it turns it back into salicylic acid anyway. But you expect this to be acidic because of the carboxylic acid proton. It to be somewhat acidic. So let's find out. Just like that. And they're just going to dip it into where their sample is and read it. And you want to read it immediately. You don't want it to sit because this paper is air sensitive, water sensitive. So it might start out red. You come back in 10 minutes, it's blue. So you want to read it right away. And then just record on your paper what your pH is. And then whatever you got for 11, that's what we're going to put in the chat. So you get for 30, we'll put that in the chat. For 106, we'll put that in the chat. Y'all, we can work with off those values. So there's the whole thing in it? Just the tip, just the edge of it. Orange? It didn't change much, did it? So where are we? So it's orange, kind of right there, about 4. Let me see. Let me show them so they'll know. So this is the pH meter or the pH guide, and this is the strip after she dipped it. So it looks like it's close to about a 4. All right. So I can save us a few seconds here because all of the samples had the same pH. So whether you have sample 1, 2, or 3, the pH is going to be 4. So you can fill that part into that data sheet. Right, none of the samples deviated from that. And again, this is, while it's quantitative, it's better to measure pH with a pH meter. Because again, the paper could be old, it could be have hydrated. I mean, there's a lot of other factors that could cause that number to be off. So the best way to measure pH is to dissolve your sample up in a solvent and then test it with a pH meter. But this is a quick and dirty way to do it. Expect it. Somewhere between 3 and 4. You expect that. Because again, on aspirin, you got this free carboxylic acid that is acidic. I mean, those proton is transferable. So go ahead, group. About the same, about 3 or 4. Same for that one. And again, this is the guide right here, so we can match it up. Yeah, about the same. So we're looking at each one of the samples having a pH ranging from 3 to 4. So it doesn't matter which one you pick. 30, 11, 106, doesn't matter. They all have a pH of about 3 to 4. All right, so the last part of this is the melting point. And I sent a video dealing with how to take the melting point using a melt temp. And one of the things we talked about yesterday, which is very important for taking the melting point, is to ensure that when you take the melting point, you don't keep the temperature the same, right? You want to, the way to do it is to ramp up initially. And then when you get about 20 degrees outside of the melting point for aspirin, you turn it down so that your temperature increases at about 2 degrees per minute. And so you want to do that. You want that to be slow and methodical so your melting point can be accurate. And it's really not a point, it's a range, because you take the first temperature you're going to take is when your aspirin first starts melting. And then when it's fully liquefied, you'll take that temperature, and those two temperatures, they'll give you a range. And so we call it a melting point, but it's really not a point. It's two temperatures between which your aspirin begins to melt and it stops melting, or finishes melting. And this is a characterization method. If you look up aspirin's melting point, is somewhere around 135 degrees Celsius. So if you know that's the melting point, when you check your sample, the closer you are to that melting point, the more pure your sample is. The further away you are from that melting point, then the more impure your sample is. And this is, again, before we had NMR and infrared and UV and all these other fancy instruments. This was one way to determine if your compound was what you said you had, would be to check the melting point. And actually, I was telling the class yesterday, this is one way that Percy Julian, who was a notable, highly notable organic chemist, African-American organic chemist and entrepreneur, he disproved a synthesis. One that was I can't remember the chemist, but he was British, and he wrote a paper, published a paper, and said, I made such and such compound, and these are the characteristics. This is the melting point, this is the TLC data, so on and so forth. And then Percy Julian synthesized the same compound, but the melting point was different. But he knew he had the right compound. So what he did was he wrote a paper himself refuting the other guy's publication, because he said there's no way you had that, because that's the wrong melting point. So it was a very important characterization method. And if you don't have other means of characterizing compounds, it's actually very effective. So we can just jump right up here. Do the melting point with this instrument right here. It's called a melt temp, right? And so the way we use the melt temp is very simple. First, we gotta plug it up, obviously, because it's electric. And then after that, what we want to do, the way you measure the melting point, if you watch that melting point video, hopefully you did, you ramp the temperature up until you get about 20 degrees away from your melting point. Who looked up the melting point for aspirin? That's Fahrenheit. So about 135 Celsius, right? Okay, so we're expecting 135. So we're going to ramp up the melt temp using this little dial right here. It's very rudimentary. We're going to turn that dial to about 4, somewhere about 4 or 5. Don't do it yet because you don't have your sample in. And then when the temperature gets to about 115, we're going to turn it down to about 3.5. And that way it'll slow down the temperature increase. Because once you get to about 20 degrees out, you want to increase the temperature about 2 degrees per minute. This is very tedious and time consuming. So we got 3 melting point capillaries, and we're going to put some sample into these. I'm going to take one of them and put some crude in it for each. So normally when you do the melting point, you need something to compare your pure sample to, and that's the crude. So we'll take some crude aspirin, take the melting point of that, and then we'll take the pure aspirin and take the melting point of that, and then compare them. On the data sheet, there's space for you to list 2 trials, but we're only going to list 1. All right, so the first will be the crude, and then it'll be samples 1, 2, and 3, and what their melting points are, the pure melting points.
Each one of you. So you're gonna measure your pure stuff against the crude. You expect the crude, you see that the crude will have dark purple in terms of crap. So it's not gonna melt at 135. It should melt way before that because it's full of crap. The more pure it is, the closer it's gonna be to that 135 expected temperature that you looked up. All right. So we're gonna take some sample and I'm gonna show you this. Normally, you have a tube that you can drop your melting point capillary down in to get the aspirin to settle. What you don't want to do is jam it into the aspirin because if it gets stuffed, it's not going to go down. So let me show you what to do first and then we can take it from there. Man, this thing needs to turn down more. All right, so that's my crude aspirin. I'm going to take my capillary and I'm just going to dip it in here on the open end, not the closed end. I'm just gonna dip it in, and you can see I got aspirin in the tip. Can y'all see that at home for your viewing pleasure? Just tap it on the bench top, just like that. And you just keep tapping it until you can see a little bit of the aspirin has gone down, but not all of it. So you just keep tapping until you get it to the bottom.
So with the capillary tubes, you want to about a 1/2 centimeter of sample in there, because when you put it, when you'll see in a second, when you put that capillary into the melt temp, you need to be able to see your sample. So you don't want it too little and it melts before you can even see it, like what's happening. So you want about a 1/2 centimeter of sample in that capillary before you put it into the melt temp.
You want to have it about 1 centimeter, maybe a 1/2 centimeter from the bottom. That way, when you put it into the melt temp, you can actually see it. That's the purpose for the amount. Right, so y'all see how that got to the bottom? Just by a little finesse and a little tapping. So that's what we're gonna do. So I'm gonna put a little bit more in here because that's not quite enough. And again, you don't want to jam it because if you do, then it's gonna get stuck at the top and it won't move. That little circle that can y'all see that? Inside of that, yeah. Just like you see those little grooves in the melt temp. So you kind of ramp the temperature up and you look through that viewfinder to see if your sample is melting. It's very important when you're doing a melting point to write down the initial temperature when your sample starts to melt, right? So if it starts melting at 120 and it stops at 128, that's what you record as your melting point, right? Because it's really a range and not really a point. So there's a range of temperatures that your aspirin is going to melt over and not just a single point. Can y'all see that sample, that tube that's in there? Can you lift up on that a little bit just to see if we can see it, if I can see it moving in the cameras? Yeah, there you go. Can y'all see that?
Yeah.
Okay, that's one sample. So we're going to load the other 2 samples in, and then we're going to wrap that temperature up, and when it starts melting, we're going to wrap the temperature down and slow the heating down so we can get a good, accurate melting point, right? So this is like watching paint dry. But I'm going to try to get another shot of all 3. If y'all can see that, she has all 3 of her samples loaded.
So taking that melting point, it's actually a very tedious process. And I've been teaching this class, oh my gosh, I don't know how many years. And it always never fails to happen that somebody would kind of drift, stop paying attention and look up and your sample is melting. So it requires a lot of attention. But again, once you get about 20 degrees outside of the melting temperature, you can really focus in. You don't have to sit there and just watch it the whole time. But undoubtedly, every semester, somebody will look away or start talking, holding conversation, look back, everything is melted. So you have to pay attention to detail with a process like this.
So you can see right here, that was a solid, and now it's kind of, let me see. And now it's fully liquefied, so that's what you're looking for through that viewfinder. And the crude for 11 was started at 110 and ended at 115. So that's
okay. So in your data sheet, no matter which sample you're using, because we use the same crude sample, in this case, we compared all of our samples to the same crude sample. So that's what you're going to put in for the melting range for the crude sample, 110 to 115. All right, that's for everybody, whether you're using sample 1, sample 2, or sample 3. The crude is the same for everybody.
And that's for the crude column?
Yes.
Okay.
All right, and that's all samples. Sample 1, sample 2, or sample 3. You can put in for the crude 110 to 115 degrees Celsius.
About 20 degrees off the expected melt temperature.
Yeah, and you expect that to be off, right? Because the crude is dirty, has a bunch of other crap in it. And so if the melting point of the pure stuff is 135, you don't expect the crude unless the reaction went to about 90% completion. You don't expect the crude to have the same melting point. You expect it to be off on purpose, right? Because it has impurities, and those impurities affect the physical properties.
Let me see if I can let y'all see this. I don't know if I'll be able to see that, but everything in there should be, come on, camera, liquefied. Can y'all see that?
All right, so if you're using sample 1, the pure melting point, and only one trial, no, it says 2 trials on the handout, only one trial. If you're using sample 1, the melting point is 134 to 136, right? If you're using sample 2, that melting point is 130 to 135. All right, and if you're using sample 3, that melting point is coming up 120 to 128.
And you put this for trial 1?
Yes.
Okay.
Mm-hmm.
And we don't have a trial 2, correct?
Right, there's no trial 2. That's correct. All right, any questions? So 120 to 120, and I'm going to send this out after the class. I'll send an announcement with all the data in it, but are there any questions at this point? So sample 3 is 120 to 128, sample 2, 130 to 135, and then sample 1, 134 to 136. And just like that the purple color test indicated, sample 1 was the lightest out of all of the 3 samples when you treated it with iron chloride. And if you look at the melting point, it's also the one that's closest to the expected melting point, right? 134 to 136 is about as close as you're going to get to aspirin, which is 135. All right, any questions about anything else?
What do we fill in for the pure melting point?
Yeah.
What sample?
For me, it's 1.
Okay,
But
so you'll put these numbers in right here. In trial 1, 134 to 136. Right, you have the crude, right? 110 to 115.
yes.
Okay, so if you're using sample 1, this is the number that you would use.
So we put this for trial 1 and pure?
No, just okay. Let me go back to the data sheet.
No, pure is the title. You just put it in trial 1.
Yeah, the title above it, it just says melting point, crude and pure, and then you're gonna just fill in the numbers for trial 1, and with the crude 110 to 115, and on the right side, trial 1 for the pure is gonna be 134 to 136.
Okay, thank you.
Yeah, no problem. All right, then if you use sample 2, it was 130 to 135. Is that right? And then if you use sample 3, it was 120 to 128. All right. Other questions? Any other questions about anything?
Is the lapses are due like by 11:59 tonight?
I'm going to extend that time because some people have had trouble getting them to load. So just finish it when you can. And,
okay.
and let me suggest this also. If you're using Chrome, try using Firefox as the browser. That may help.
Okay, yeah, because I was having some issues with Chrome last night, but it ended up working. And I was trying to upload my little certificate thing for the first 2 because I just got access to a computer.
Okay.
And it wasn't allowing me. It was just saying unable to submit.
On Blackboard?
Yes.
Yeah, let me double check because what I could do for that is I could just add a second attempt to the assignment. I can do that now. And then that way you'll be able to upload it. So hold tight.
Okay, thank you.
Yeah, no problem. No, wrong.
I have a question too.
Yeah, go right ahead.
Okay, what's the total amount of ethanol used?
What did we say? Can somebody answer that who had that filled in? I think it was, I want to say it was 15, 25 max or something like that. I know the maximum was 25, but I can't remember the number that I gave you all. But somebody may have that written down. You can tell us. Which lab store was it that you were trying to submit the certificate for?
Chemistry safety and organic chemistry introduction.
All right, hold on. Let me just add a second attempt. Yeah, I can't remember. I'll go back and I'll pull up the announcement in a second because I think that I sent that value out. Submission details. All right, so that one you can try to resubmit it. And then you said organic chemistry introduction.
Yes.
All right. All right. Let me look at the let me pull those announcements up and see where I know I sent that number out. I want to say it was like 12 meals or 13 meals, something like that. But hold up. Let me scroll back through there. 14. It's right. Which sample are you using? Do you know? 1, 2, or 3? I don't know who that was that asked me about the amount of ethanol, but I have it right here. If you're using sample.
Well, I needed it too. I needed it for sample 3. I don't know who asked either. 15
milliliters for sample 3. Sample 1 was 12 mils, and then sample 2 was 15 mils also. Yeah, I sent this on the 14th of.
I'll send it in the group me for whoever needed it.
Yeah, and if not, it's in the announcements in Blackboard for September the 14th. All the data from that recrystallization lab is in there. All right, other questions? All right, if not, then I'm going to stop sharing and stop recording. And we'll be done for the day. I'm gonna set up the